Okay, so we're going to do another example for car payments. Suppose you are purchasing a car for $24,000. You pay a $2,000 down payment, which means you pay it as soon as you collect your car. So the part that you plan to finance is going to be the $24,000 minus the $2,000 down payment, and you're only going to finance $22,000 on the car. So if you paid the car up today, you would owe $22,000, so the present value of the car is $22,000. But you don't have $22,000, so you have to go to the bank, which gives you a loan with 7% interest rate for 60 months. And you want to know how much your car payments are going to be. Okay, so let's go ahead and use our formula. We have P, which is the present value, and which is $22,000. That's how much the car is worth today. That's how much you're financing. The recurring payments, all capital R, is I don't know. That's what we were trying to figure out. The lowercase r was the 0.07, which is the 7%. The 60 months, this is a little tricky. 60 months is actually the total compounding periods, which is N. Another way you can think about 60 months is 60 months divided by 12. That gets you 5 years. So time is 5 because time has to be 5 in years. And then N would be 12 times 5. It's kind of redundant. It's probably easier if you just know that it's 60 months total, not the value for T. So M is your monthly payment, so you're paying 12 months in a year, and then I would be 0.07 divided by 12. Now 0.07 divided by 12 doesn't reduce nicely, so we're just going to probably leave that as a fraction right there. I'm going to plug this in my formula. We have P, which is $22,000, equals R, my recurring payments, times that large parentheses, then I have a bracket, 1 minus 1 plus I. The I was 0.07 over 12, raised to the negative n, which was negative 60, then it closes that bracket, divided by I, which is the 0.07 divided by 12. Make sure you keep parentheses around that denominator because you want to make sure that that stays together until you get that last parentheses in. Now, because I'm trying to work this out and I'm solving for R, and R is not already by itself, so what I'm going to do is I'm going to use the 22,000, and then I would like to simplify or reduce the parentheses here. So I'm going to go ahead and type that parentheses in. Parentheses, then a bracket, 1 minus parentheses 1 plus 0.07 divided by 12, close that parentheses, raise it to the negative 60. Now I have to get out of my exponent and then close that bracket. So that's the numerator. Now I'm going to divide by parentheses 0.07 divided by 12, close that parentheses in the denominator, and then one last big parentheses that finishes out the entire expression. When I hit enter, I'm getting 50.50. Now this keeps going 19935. If you truncate 50.50, you're not going to get the exact right answer. So what I want you to do is to figure out how to store this value in your calculator. You're probably looking for a store key or a save key. In this case, mine is STO and then a little arrow. So I'm going to store this answer as a variable. Now, right above the store key is the X, Y, Z, T variables. So I'm just going to go ahead and store this as X. So that means anytime that I use the variable X in the future, it's going to be 50.519935. It's not going to be truncated at all. To solve for R, I want to divide by that 50.50, but again, I'm not just dividing by 50.50, I'm going to divide by that stored answer. So I'm going to take the 22,000 and divide it by my stored answer, which I stored in as X, and that gets me R, my recurring payment, is going to be $435 and we'll round it up, 63 cents. Okay. Now, if you chose not to use the store key, if we do 22,000 divided by 50.50, and we truncated it right after that 0, do you see how it's really close, but it's not exactly the same? This one would you would have $435 and 60, probably round up, 5 cents. So because if you truncate it, you're going to be off a couple cents, which in my math lab is going to count it wrong, which could be a little bit frustrating. So if you use a store key, then you shouldn't be getting those problems wrong. Now, how much interest did we pay for that first month is a very interesting question, because not only in these recurring payments are you paying towards your $22,000 that you owe, but you're also paying interest. So some of the payment goes to interest and some of it goes to the balance. So let's see if we can figure that out. So for interest, we're going to find the interest by taking the present value times I, which is the interest rate per period. And that's going to tell us what the interest is going to be for that first payment only. So if I take 22,000 times that 0.07 over 12, I'm going to use my calculator for that. 22,000 times 0.07 divided by 12. That gets me $128.33 of interest every month. So what goes towards the balance? Well, to get that, I'm going to take my recurring payment minus the interest, and that's going to get my towards the balance. So I'm going to be paying $435.63 minus $128.33 for my interest. Now you can truncate here because everything has to round to the nearest penny. We don't have anything smaller than a penny. So that gives me $307.30 towards the balance. Okay? So what is the balance after this payment? Well, you originally had a balance of $22,000. After you paid your $435 payment, of which $128 went straight to the bank, and only $307.30 went towards your balance. If I take the $22,000 and I subtract off what went towards the balance, on my next month statement, it's going to say you owe $21,692.70. Okay? Now you're going to pay your $435 every single month. The payment stays the same every single month. But what part goes to the interest and what part goes to the balance actually ends up changing. So let's do one more month. What does the interest do for the second month? Well, the interest, again, is equal to the present value times I. Now, our new present value is $21,692.70, and we're going to multiply that by 0.07 divided by 12. So I already have the 21,000, so I'm just going to hit multiply by 0.07 divided by 12, and that gets the interest for the second month as $126.54. Now, this is different than the first month's interest. The reason it's different is because you owe less, and so you owe less interest. How much now is going to the balance? Remember, you still paid the same exact $435 recurring payment. So I'm going to take that recurring payment minus my new interest, so $435.63 minus the interest that I paid for the second month. And that gets, let's see, 435.63 minus 126.54, and that's going to be $309.09. So for the first month, only $307 went towards the balance, and the next month, $309 went to the balance. So as each month progresses, you're paying more and more part of your payment goes towards the balance, and less part of your payment goes straight to the bank. So note that since the balance is different after the first month, the interest for the second month is less than the interest for the first month. Because the payments are staying the same, different amounts are applied to the principal and the interest each month as your balance decreases. And this is good for us. The next thing we're going to talk about is amortization. A loan is amortized if both the principal and the interest are paid in a sequence of equal periodic payments, like the car loan example that we just talked about. We can solve the present value of an annuity formula for R to create a new formula for payments. So let's do that right now. What we're going to do is we're going to multiply the big parentheses by its reciprocal. So everything in the top goes to the bottom, everything in the bottom goes to the top. If you do it to one side, you have to do the same thing to the other side. Notice that the numerator and the denominator divide out to 1 on the right-hand side, and the denominator and the numerator also divide out to 1. So on the right-hand side, we're just left with R. On the left-hand side, I'm going to put the P in the front. P times the I over bracket 1 minus 1 plus I to the negative n bracket. And this is the same formula that we had used above, but instead of solve for P, it's now solved for R. If I wanted to redo the same problem, it would be a little bit easier to use this formula that we just used in our car payment problem. We wouldn't have to use the store key because all of the values would be on the same side of the equal sign. So you could just go ahead and type it in the calculator all at once, which would make this one a little bit easier.